Hello, everyone. Welcome to a new session of the O'Higgins Seminar on Optimization. And welcome all. Today is my pleasure to introduce Henk van Waarde. Sorry if I mispronounced your your last name. My Dutch is kind of rusty. I didn't know it was that good. So Henk is professor in the University of Groningen in the Bernoulli Institute of Mathematics, Computer Science, and Artificial Intelligence in the group of Systems Control and Optimization. And today he's going to give us a talk about data-driven stabilization using prior knowledge of uncontrollability and stabilizability. So, Henk, the stage is yours.
Yeah, thank you very much, Juan Jose, for the nice introduction. So I do realize that this is, of course, an optimization seminar, so that the topic may be slightly different from what you're used to. Indeed, I'm working in the systems control and optimization group. My background is mainly in systems and control theory, although there are, of course, very strong connections between control and optimization. So what I want to talk about today is data-driven stabilization. So how to find stabilizing controllers using data, but also incorporating prior knowledge about the dynamical system. So this is based on some recent work that we've been doing. So I want to start by giving you just a small introduction to what data-driven control is. So imagine that we have some dynamical system over here that we want to control. Now, in system and control theory, an established approach to do that is to first build a mathematical model of that dynamical system. And there are basically two ways of doing that. So one could use, for instance, first principle modeling. So this is using, for instance, Newton's laws or the laws of Kirchhoff to come up with the mathematical model of the system. Or alternatively, in case the physics of the system is not so clear or some of the parameters of the system are unknown, one could also use data. And the process of using data of the dynamical system to find a mathematical model, that is typically called system identification. Once one has a mathematical model of the system, one can use the plethora of systems and control techniques to find controllers of the dynamical system using the mathematical model. Now, in data-driven control, we're interested in an alternative approach to find controllers of the dynamical system. And in data-driven control, actually, we want to use the data directly to find a controller. That means that we try to avoid this intermediate step of system identification. So we do not go through a mathematical model of the system, but instead of that, we directly go from the data to a controller of the system. Now, there are two basic reasons why one would like to do that. So the first reason is that bypassing system identification can be beneficial from a computational point of view. So you require less computation because you do not have to compute actually a mathematical model using the data. And this is one potential benefit of this direct approach to data-driven control. But another potential benefit is that sometimes it's possible to find controllers using data when it's impossible to find uniquely a mathematical model using that data. So in that case, the modeling step fails, but still you can find certain controllers using the data. That's a more fundamental reason why direct data-driven control is important.
Sorry, Henk,
Yeah.
can I interrupt you for a bit? Are you moving the slides? Because we're seeing the first slide, the title. You were.
Okay. Good that you pointed out. So
Yeah, don't worry.
clearly went wrong here.
We will still follow you.
Try to reshare my screen.
Yeah, don't worry.
Maybe you should check then whether I can move. So
Yes,
if I do this, do you see that?
now it's moving. Now it's moving. We can see it.
Now
Yes.
it's moving. Okay, perfect. Okay.
Yes.
Yeah, so I was talking about these two benefits of direct data-driven control, right? In particular, in today's talk, I want to focus on data-driven stabilization approaches. And there I want to specifically find a stabilizing controller using the data. Now, there is some previous work on this. So for instance, in the paper by Claudio de Perzes and Pietro Tesi, they find stabilizing controllers using persistently exciting data. And here they indeed circumvent the step of system identification, which means that they address the first potential benefit. But one can show that using these data, it is still possible to also identify a model. So in principle, then the second benefit is not covered. In the same year, we also worked on this problem of data-driven stabilization. And in this paper, we found necessary and sufficient conditions for data-driven stabilization. Also showing that even in cases where a unique model identification is not possible, it's still possible to find a data-driven stabilizing controller. So that also addresses this second benefit. Now, in terms of prior knowledge, there's not so much work in data-driven control. So sometimes in addition to using data, people have also incorporated known bounds on the system parameters, or studied the situation that some of the parameters of the system are exactly known, but this is basically all the work on prior knowledge that there is. This is a little bit in contrast to system identification, where there's actually a lot of work on prior knowledge. So for instance, prior knowledge on stability, eigenvalue constraints, positivity, and passivity properties of the system have all been studied. So motivated by that, I'd like to also develop a theory for data-driven control, incorporating prior knowledge. In this talk, in particular, I want to study data-driven stabilization using prior knowledge on controllability and stabilizability, so two system theoretic properties. So before I dive into that, I want to give you a bit of a background on the problem of data-driven stabilization to make the talk as self-contained as possible. Then I will state the problem formally. I will treat both controllability and stabilizability. And finally, I'll also close with some results on experiment design. So let's start with the background. I'm considering a very simple class of dynamical systems, the following form. So U is the input and X is the state. And A true and B true are unknown system matrices that are the model of our unknown system. So the matrices A true and B true are not known to us, but we do collect data obtained from this system in the form of measurements of the input and the state of the system. So I collect these matrices containing T samples of the input and T+1 samples of the state. And I collect that in this data set D. So my overall goal is to use that data, D, to find a stabilizing feedback law, so U is Kx, such that the closed loop system obtained from interconnecting this controller U is Kx with this unknown system is asymptotically stable. And that's my overall goal. So I want to find a stabilizing controller, basically. That's known to be equivalent to finding a K such that A true plus B true K is sure. So has all its eigenvalues within the unit disk. So that's my goal. But now here's the kind of twist, because based on the data, of course, we don't know what A true and B true are. But if I define these data matrices, so I define X minus, U minus, and X plus, like this, then you can quite easily see that the true system matrices are related to the data via this linear equation. So in particular, X plus is equal to A true times X minus plus B true times U minus. But A true, B true are in general not the only solutions to this system of linear equations. So I capture all solutions within this set sigma D. So sigma D contains all pairs of matrices A and B, such that this linear equation is satisfied. Note that in particular, the true system is also a member of sigma D, but there may be many other systems. So now we can formally state the data-driven stabilization problem, because since we don't know which system within sigma D is the true one, my problem basically boils down to finding a controller that works for all systems in sigma D. So that's formalized here. So given the data D, my goal is to find a controller K such that A plus BK is sure for all A, B, and sigma D. That's the goal. And again, the reasoning behind this is if we can find a controller that works for all systems consistent with the data, in particular, it also works for the true system. Okay. So that leads us to this following notion of informative data. So basically, I say that the data D are informative for stabilization if such a controller exists. So if there exists a K such that A plus BK is sure for all A, B, and sigma. Now the question is, of course, how can I know that my data are informative? And given some informative data, how do I find the controller K? So let's study this following proposition. And this is from the paper that I showed you before, which says the following. So the data D are informative for stabilization if and only if the rank of X minus is N. So X minus has full row rank. And there exists some right inverse of X minus such that X plus times that right inverse is sure. So this is a necessary and sufficient condition for data informativity. And moreover, the proposition says that the following. So in this case, so if you have informative data, then also K is U minus times that right inverse is in fact a stabilizing feedback gain. So that's how you can find K.
Sorry, Henk, for interrupt you.
Yes,
I
sure.
blink a moment and I missed the definition of X or X minus. I don't know.
Oh yeah, sure.
Can
So
you
it's
repeat,
here.
please? Okay, but that is
So
the
X minus
trajectory. Okay,
contains the state samples from 0 to t minus 1.
which is data is known, of course, right?
Yes, indeed. Yeah. Yeah, so both of these matrices, X minus and X plus, are known. So
Okay,
X plus is simply a shift of the
perfect. Thank you.
yeah. Yeah. Yeah, so yeah, basically, indeed, then, so given these data matrices, I simply check whether there exists a right inverse, such that X plus times that right inverse is sure, and that right inverse multiplied with U minus, so the input data, then also gives me a stabilizing controller. Okay, let's consider a simple example of this. So here I collect 3 samples of the state and 2 samples of the input, like this. And thus the X minus and X plus matrices are given over here. So remember, X minus is simply all columns of X except for the last part. X plus contains all columns of X except for the first part. So these are X minus and X plus. I now notice that, of course, X minus is square. There only exists one right inverse in this case, which is simply equal to the inverse. And computing X plus times the inverse of X minus then gives me this matrix, which you can easily see is sure, or eigenvalues within the unit disk. So indeed, the conditions of this proposition are now true, which means that this controller that we find over here actually stabilizes all systems consistent with the data. And in this particular example, that system set sigma d is given over here. So one thing to note from the example is that there are many systems consistent with the data, so it's not possible to uniquely identify a system model, but still you can find a stabilizing controller that stabilizes all these systems consistent with the data. So that's already interesting. Okay. Then as a follow-up remark to this proposition, you may wonder in general how to compute this right inverse X minus dagger. Of course, in the example, it was simple because X minus was square. In general, it's not. But you may use the following linear matrix inequality to compute a suitable right inverse. So the steps are as follows. First, you find the theta matrix, T by N, that solves this linear matrix inequality. Then you set this particular right inverse of X minus, so theta times the inverse of X minus theta. And then finally, this recipe for the controller works. So in general, even if X minus is not square, this recipe can yield you a suitable right inverse. So not all right inverses of X minus work. You of course need this property that X plus times the right inverse is sure stable. But this is a way to compute the right inverse. Okay. Yeah. There are, by the way, also other LMI conditions. This is just one example of an LMI condition. Just note that here the variable theta has size that depends on the horizon of the data that we collect. So it depends on t. But there are also alternative LMI conditions where the size of the variables does not depend on the time horizon of the experiment. And that can be beneficial for larger data sets. Okay. Yeah, so with this small piece of background, I now go to the problem formulation. So remember that I want to include both data as well as prior knowledge of our system in the data-driven stabilization. So to capture that in a sort of mathematical framework, I now denote this set sigma pk containing all systems that comply with our prior knowledge. So sigma pk is just some subset of M that captures our prior knowledge. In particular, the true system, A true, B true, must then be a member of sigma pk. Now, so sigma pk is just some set of systems for which I know that the true system lies within that set. Okay. Now, based on that prior knowledge, I change now the problem formulation. So before we wanted to find a controller that works for all systems consistent with the data. Here the problem changes a little bit. So given the data D and this set of prior knowledge, sigma pk, the goal is to find a controller K such that A plus bk is sure, stable, for all AB, not in sigma D, but in the intersection of sigma D and sigma pk. So what does this mean? It means that I want to find a stabilizing controller that works for all AB systems consistent with the data and the prior knowledge. That is the goal. Now, hence, I'm looking at the intersection here. Using this problem formulation, we can also change the definition of informativity. So in particular, I call my data D sigma pk informative for stabilization if there exists a controller K such that A plus bk is sure for all AB in this intersection. So the data are informative whenever I can find a suitable controller using the data. Notice that the previous notion of informativity can be captured using this particular definition by setting sigma pk to be M. And in that case, we do not have any prior knowledge, and the definition boils down to the previous definition. But of course, now our task is to characterize sigma pk informativity for different types of prior knowledge. So that's what I will do in the rest of the talk. In particular, I focus on two types of prior knowledge, namely the cases where we know that the system is controllable or stabilizable. So I set sigma pk either equal to the set sigma cont or sigma stab, where sigma cont denotes all systems that are controllable, and sigma stab are all pairs AB that are stabilizable. So just to remind you what are controllability and stabilizability again, I have the definitions here. So we call a pair AB controllable if the reachable subspace of that pair is the whole space. So the reachable subspace of a pair of matrices AB is equal to the image of B, AB up to A n minus 1B. And whenever that subspace is equal to the whole space, we call the pair AB controllable. The interpretation of that condition is that you can reach all states from the origin by choosing a suitable sequence of inputs. Now, in that case, we call the system controllable. And moreover, we call AB stabilizable if there exists some f such that A plus BF is sure. So whenever there exists a stabilizing controller for AB. So, well, I want to now characterize this sigma pk informativity for these two types of prior knowledge, stabilizability and controllability. But notice that this is in general much harder than the original problem where we only worked with the set sigma d. The reason is that sets of controllable and stabilizable systems are not convex, meaning that this intersection of this affine set sigma d with sigma pk is also not convex. So we're trying to find a single controller that works for this whole non-convex set. In general, that's a hard problem. And also in this case, it turns out to be hard. But still, for these two specific types of prior knowledge, we can come up with conditions. So I'll do that in the rest of the talk. Before I go to the results, though, let me show you one more motivating example, just to show you that indeed this prior knowledge can help in data-driven stabilization. So let's consider this example. I have 3 samples of my input, captured in this matrix U minus, and 4 samples of my state. That means that the matrices X minus and X plus are given over here. In this case, you can also write down the set sigma d of all systems consistent with the data. And they turn out to be all these pairs of AB matrices. Also, one thing to note is that the data are not informative for stabilization. That follows from our previous proposition, because note that the rank of X minus needs to be full for that to happen. But in this case, of course, the rank of X minus is 1 and not equal to 2. So the data cannot be informative for stabilization. Meaning that using this data alone, I cannot find a stabilizing controller for all systems consistent with the data. However, if I now look at the intersection of sigma d and sigma stab, so this set of stabilizable systems, then that constrains the values of beta. So absolute value of beta needs to be less than 1 in this case. Which means actually that there does exist a stabilizing controller that stabilizes all systems in this intersection. In particular, I could choose k to be -1 next to 0, and you can show that that indeed stabilizes all systems within this intersection. So even though the data are not informative for stabilization without any prior knowledge, they are informative for stabilization if I make use of the prior knowledge on stabilizability. So if I know that my system is stabilizable, then in this case, I can find a stabilizing controller. So that means that indeed, in this situation, having that prior knowledge helps. It weakens the conditions on the data. For example, you don't need that the rank of X minus has to be full anymore. So, yeah, with that in mind, now I want to provide characterizations for sigma pk informativity or stabilization for these two types of prior knowledge. So this is the problem. To find necessary and sufficient conditions under which the data D are sigma cont informative for stabilization and sigma stab informative. Okay, so let's start with the results then. Let's start with controllability as prior knowledge. So we proved this interesting theorem saying the following. So suppose that the true system, A true, B true, is in fact controllable. So A true, B true is in the set sigma cont. Then actually the following statements are equivalent. So the data are sigma cont informative for stabilization if and only if they are informative for stabilization. Moreover, if K is a stabilizing controller for all systems within this intersection, so for all AB in the intersection of sigma D and sigma cont, then that controller is also a stabilizing controller for all AB in sigma D. So when a controller stabilizes all systems in the intersection, it also stabilizes all systems within sigma D alone. So the interpretation of this is that controllability as prior knowledge does not help because informativity is equivalent to sigma controllable informativity. So knowing that your system is controllable does not help you to find a stabilizing controller. So that's also an interesting result. Yeah, so just to give some intuition why this is true, this theorem is based on 2 lemmas. The first one says the following. So let Mn be a controllable pair. Let M0, N0 be any pair of matrices of suitable sizes. Then, in fact, the pair M plus alpha M0, N plus alpha N0 is controllable for all values of alpha except for at most N squared values. So for almost all values of alpha, this is in fact controllable. You can see why this is relevant in the context of this theorem by applying that lemma for the true system as M and N. In particular, that is assumed to be controllable, so that satisfies the condition of the lemma. And for any M0, N0, in the left null space of the X minus U minus matrix. In that case, you can show that for any alpha, this pair of new matrices, M plus alpha M0, N plus alpha N0, is still a data consistent system. And the lemma shows that then almost all of them are controllable. Okay, then how to prove the theorem? Well, that's using the second lemma, which says the following. So if we take any real epsilon, F a finite set, and Mn real n by n matrices, such that m plus delta n is sure, for all delta within this interval, excluding this finite set of values. Then actually one can prove that m plus delta n is sure for all values of delta. And that's actually how you can show that this controller stabilizes not all controllable systems within sigma d, but in fact all systems in sigma d. So that's indeed how you prove the theorem. But the bottom line is really that controllability as prior knowledge does not help. So sigma cont informativity is equivalent to informativity of the data. Okay. So that's treats the controllable case, but let's now consider the stabilizability case, because here the situation changes, as we saw already in the previous example. So in the case of stabilizability as prior knowledge, we also proved the theorem. It says the following. Suppose that the true system is now stabilizable, and the data are sigma stab informative for stabilization. This theorem will then provide necessary conditions for sigma stab informativity. Because then the following two statements hold. First of all, the image of x plus must be in the image of x minus. And secondly, if the rank of x minus is less than n, then this image condition must hold. So it must be true that the image of x minus u minus is equal to the image of x minus cross Rm. So this is interesting because this image condition actually implies that B true, so the true B matrix, can be uniquely recovered from the data, but not necessarily A true. We can also compare this theorem now to the case of informativity without any prior knowledge, because remember that in that case we needed x minus to have full row rank. In other words, the image of x minus must be the whole space, Rn. In comparison to that, in the case of sigma step informativity for stabilization, one does not need that the image of x minus is the whole of Rn, but it must be true that the image of x plus must be in the image of x minus. And in the case that we do not have a full rank x minus, this image condition must hold. So this is a necessary condition for sigma stab informativity. Based on that necessary condition, we also managed to prove a necessary and sufficient condition. So that's given in this following theorem. So suppose that A true, B true is again stabilizable. Then we distinguish between two cases. First, if the rank of x minus is n, then there's nothing new. So D are sigma stab informative if and only if they're informative for stabilization. So in this case, actually having the prior knowledge on stabilizability does not help. But interestingly, what can also happen is that the rank of x minus is less than n, and then the data are sigma stab informative for stabilization, if and only if these two necessary conditions hold. So it turns out that in that case, the necessary conditions that we treated before in A and B turn out to be also sufficient. So in particular, D are sigma stab informative for stabilization, if and only if the image of x plus is in the image of x minus, and this second image condition holds. Okay. So the conclusion is that really prior knowledge on stabilizability can be very helpful in the case that the rank of x minus is not full. Okay, let's also treat an example, and let's go back to the example that we studied before, so our motivating example. It was a case where U minus was given here, and X minus and X plus are the data matrices here. So note that both the image of X minus and the image of X plus is equal to the image of 1, 0, which means that indeed the image of X plus is contained in the image of X minus. And also, if you compute the image of X minus U minus, it's equal to the image of this matrix over here, which is indeed equal to the image of X minus cross R. But it shows that indeed the two conditions in the previous theorem, in the case that, of course, the rank of X minus is not n, the two conditions 1 and 2 are satisfied. So from the theorem, we can then indeed conclude that the data are sigma step informative for stabilization. Okay. Just a little bit more discussion on this theorem. So notice that we distinguish between these cases, that X minus has full rank and has rank less than n. Well, that second condition, so the rank of X minus less than n, is very important, especially in cases where your true system is not controllable. Because in such cases, for example, when you start in x0 is 0, then the rank of x minus is always less than n, no matter which input sequence you apply. So, yeah, even if you collect arbitrarily long data trajectories, no matter with which input, always the rank of x minus will be less than n. So it's important also to have conditions in that case. And the previous theorem then shows in which cases you can still find a stabilizing controller. Okay. Yeah, we also came up with LMI conditions for actually constructing a stabilizing controller, but I will not go into too many details there. If you're interested in that, we wrote a paper on that together with Amir, Trem Baltussen, and Maurice Hemels. Okay. Well, let's consider another example. So I have this illustrative example of a 3-tank system. So there's this basin at the bottom, and the control input corresponds to allowing flow from the basin to tank 2. That means that the water level x3 in tank 3 is not controllable. Because, yeah, I cannot flow any water into tank 3. But this is still an example of a stabilizable system. It's not controllable, but it is stabilizable. And a discretized version of this model is given by these matrices A true and B true. So what do we do? Well, we perform Monte Carlo simulations. We have 1,000 scenarios. For each scenario, we simulate a system from t is 0 to t is 100. The inputs and initial condition are drawn randomly from a Poisson distribution. And we use part of this data set to do the analysis. So I construct parts of the data set with 3, 4, 5, 10, and 100 samples, and I perform an analysis based on this partial data. So the results are given then in this table. So if you look at the first column here, this is the percentage of trials, so the percentage of this 1,000 trials that we did, for which the data are informative for system identification, meaning that I can identify a unique model from the data. You can see that by increasing the length of the data, indeed, the percentage also increases, but it stabilizes around 63%. We also studied informativity for stabilization. So when we were interested in finding a stabilizing controller, First, in the case without any prior knowledge, so in that case, sigma pk is M, the full space. There already you can see that, for instance, using 3 samples, in 8% of the cases, you can find a stabilizing controller, and also that percentage increases. But again, it stabilizes around 63%. But now when you include prior knowledge, so including prior knowledge on stabilizability of the system, which, by the way, in this physical system, we know it to be stabilizable because the water from tank 3 flows into tank 2. So in the limit as t goes to infinity, this water level goes to 0. So we know this system is stabilizable. If we use this prior knowledge, actually, then in 100% of the cases with 100 data samples, we can find a stabilizing controller for the system. And already with 3 samples in 42% of the cases. So using this prior knowledge really helps. Okay. Well, in the final part of my talk, then I also want to spend a few words on experiment design. So far, I only treated the question of, so given some data, how to find a stabilizing controller from that data, and when is that possible to find a stabilizing controller. Now, in the final part of the talk, I also want to discuss with you the question of how to generate informative data. So how can I choose my inputs in such a way that the resulting data are informative for stabilization? So this is formally the question that we study. Now, so given some initialization of our system, x0, how to choose the inputs u0 up to ut minus 1, such that the resulting data set, calligraphic D, is informative for stabilization. Again, involving this prior knowledge. Okay. So how to do that? Well, we came up with an experiment design algorithm. To explain that algorithm a little bit, I will denote these partial data matrices. So x from 0 up to t minus 1 denotes all the data that I collected from 0 up to time t minus 1. Similarly, also u0 t minus 1 denotes all the input samples from 0 up to t minus 1. The idea of the experiment design algorithm is now to generate inputs one by one. So I apply one input to the system, I collect again a state sample. Based on this data, I generate again a new input. And I collect again the corresponding state sample. So it's an iterative design. In particular, the algorithm that we came up with is doing this. So we initialize again our state, x0, in Rn. The first input, u0, is chosen to be non-zero. And then we apply u to the system, and we measure the corresponding state, xt plus 1. Then on the basis of the data that we collected in the past, so on the basis of the state samples from 0 up to t minus 1, we make a choice for the next u of t. So you can see in lines 5 to 12, that's how we choose the next input u of t. So it's an online design of the input. And then finally, the algorithm, after the stopping criterion is met, returns capital T, so that's the number of data samples, and a data set calligraphic D. Okay. Now, of course, the question is, what can we prove for an algorithm like this? So we came up with the following theorem. It says the following, so let D be the data generated by this online algorithm to choose the inputs. Then the time t, so this is the length of the data that we collected, is computed as follows. So it's the dimension of the reachable subspace of A through B through x0 plus m. And one can easily show that this is always less than or equal to n plus m. Now, so this algorithm terminates after a finite number of steps, basically, always less than n plus m. But more importantly, if the true system A through B through is a stabilizable pair, then in fact the data generated by this algorithm are always sigma step informative for stabilization. So the algorithm always returns informative data for stabilization. So this is actually a nice approach of collecting data, because if you design the inputs according to this algorithm, then you know that eventually, after the algorithm terminates, you have informative data. Okay. Well, finally, a remark about this. So we can also prove that this number of data samples, capital T, is actually the shortest possible data length in certain cases. So for some cases of A through B through and X0, this online experiment design algorithm is fully sample efficient. It returns the smallest number of samples, but not for all A through B through and X0, only for specific ones. Okay, well, that's with that I come to the end of my talk. So let's conclude. I have the following takeaway messages. So we looked at data-driven stabilization using prior knowledge on controllability and stabilizability. Well, it turns out that actually controllability as prior knowledge is not helpful for stabilization, but prior knowledge on stabilizability does allow us to weaken the conditions for data-driven stabilization, especially in the case that the rank of X minus is not full. In the final part of my talk, I also presented this online experiment design algorithm that generates the input U of t in an online fashion. And that always generates a sigma step informative data set. For future work, at the moment, we are considering also other types of prior knowledge, for instance, subsets of controllable systems, and also noisy data, so where my data are corrupted by noise. And if you're interested in some more of these topics, we recently wrote a book on database linear systems and control theory. You can download it for free using this QR code. And the book also contains many other topics like noisy data, but also more involved system dynamics. For example, involving also an output equation. So if you're interested, you can have a look. Last but not least, I want to thank my collaborators. So Amir Shakouri is the PhD student with whom I did most of the work. And these are the two papers that we wrote about this. So the first one is about conditions for informativity. The second one is about experiment design. And the first work was also done in collaboration with Trent Baltussen and Maurice Hemels from the University of Eindhoven. And the second work was done together also with Kanat Chamlibel from the University of Groningen. Yeah, and finally, also, I want to thank you very much for your attention. Thank you.
Thank you, Hank. Thank you for your talk, for your very interesting talk. Um, so we have, I think, plenty of time to make questions. So are there any questions in the audience?
Question?
Hector? Yeah, go
Yes.
ahead, Hector, please.
Hi, Henk. Very nice talk indeed. Yeah, actually, I have more like a general question about this application, because it's first time I see this type of application. So,
Mhm.
uh, um, you can you do something similar for continuous time
Yeah.
concepts? Yeah,
Yeah, that's
yeah. So, can you say a little bit more about that?
that's a very good question. So if we go back to the dynamics,
Mm-hmm.
right? Because there are some intricacies for continuous time dynamics. Let me see. So here, right? So a natural analog for continuous time systems would be to have some derivative of the state here on the
Mm-hmm.
left-hand side, right?
Yep.
It's then possible to also do the things that I've showed you today if one assumes measurements of the input, the state, and the state derivatives. Because then one can construct analogs of these data matrices in discrete time.
Mm-hmm.
But it's an active line of research to avoid also state derivative measurements, because one always argues that measuring the derivatives of states is prone to noise and
Yeah.
so on. But there are different approaches that actually avoid measuring derivatives of state.
Okay.
And there are a few papers on that. So, for instance, one approach is to use orthogonal bases to work with coefficients corresponding to certain basis functions
Mhm.
rather than working with state derivatives. But indeed, it's a good question. So
Okay.
it is possible to generalize this to continuous time systems, but it's not so trivial because
Okay.
of the
Okay.
measurements of derivatives.
But somehow you need to pass, I guess, you pass to the discrete time system. So you need to maybe, I don't know, discretize your continuous time, and
That,
somehow maybe you need to prove, or I don't know, or at least test that this discretization is not important. It's not, something like. It's that's what I think about. Is this the discretization itself could be noisy? I don't know. Could be
Mhm.
could affect. Right? It's
Yeah,
yeah.
that's another a good point. So, for instance, so what the line of research I was mentioning before does not go via discretization, but this is
Okay.
indeed another possibility.
Okay.
Um, One would need
Ah.
to assume something like zero order hold on the
Okay.
input to
Okay.
ensure that this discretization
Okay.
is good. Um,
Okay. Okay. Okay.
but
Okay. Okay.
that could be another approach indeed.
Yeah.
Yeah,
Yeah. Okay. So the approach is different. The approach is deal directly with the continuous time framework. Okay.
exactly.
Okay, 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 okay. That's what I was somehow lost. But
Mhm.
okay,
Yeah.
great, great, great. Yeah, thank you.
You're welcome.
Thanks. Are there any other questions from the audience? Anyone? I think I
I have
have a
I have a
little.
few, but I don't want to I don't want to ask
Sorry.
alone. Maybe you also have some questions. So.
I have one question. Maybe I
Okay,
can.
good. Go ahead.
Maybe mine is short. So then after that you can you can go back to your questions. Yeah, I mean, well, Hank, I have a little question, but you mentioned it on your future work. I mean,
Mhm.
I think as far as I could understand, only the prior knowledge that you were considering here was about the stabilization of the system, right? Yes, but I was thinking about noisy data or another prior knowledge about data, and maybe I don't know about the approach from machine learning and stuff. I mean, when you say prior knowledge about something, is that you know something about you have some intuition about the distribution of the data or something like that. So, is there any approach like that, or is like can you comment us about that
Mhm.
branch? I mean, that future question.
So in the case of noisy data, you mean, or
Yes.
yes, yeah. So what we're currently still focusing on in the case of noisy data is approaches for system identification. But there, the situation changes a little bit because in the case of noisy data, you can never or almost never uniquely identify the system. But we're working with notions of, yeah, accurately identifying the system up to some epsilon, basically. So we have some experiment design results for that also in the case of noisy data, but we're still working on it, actually.
Okay.
So the paper is still under construction. Yeah.
Okay, I see.
As for the first part of the talk that I discussed, so we do have extensions of data-driven stabilization, for instance, to the noisy case also. Um, There we work with tools like matrix versions of the S-lemma to ensure that a whole ellipsoid of systems that are consistent with the noisy data are also stabilized by a controller. So that is treated, for instance, in the book. So we do have such extensions to noisy data also.
Okay.
But for the experiment design, at the moment, we're still doing the identification in the noisy case.
Okay, okay. I see. I understand. Good. Are there, I don't know if anyone has any other question. Maybe if no one, maybe we can go back
I
to
have
Hector.
one. Sorry, I had some. Remember, I had some few questions, so maybe I can. Can I go? Okay. Okay. Actually, I
Mhm.
have maybe only one, but this somehow could have several implications. Henk, I don't know too much about. I just know the minimum about about discrete time. But I know about continuous time because it's somehow what we teach somehow, right?
Mhm.
What I teach. Of course, as far as I know, as I remember, discrete time somehow is easy in some sense because this type of computations, we can see those of things here. But on the other hand, the fact that you can deal with derivatives and all this kind of stuff in continuous time allow you to create I would say, a more robust theory, right? This is my general impression somehow, right? And you have like observability, you have whatever, you have asymptotic observers, these kind of things. This like very nice theory. And I was wondering about that. I mean, of course, maybe it's ongoing, right? But I mean, I'm not talking about continuous time case. Maybe in discrete time case or whatever is the this data-driven approach somehow can also or has already reached or can go in that direction, like observability,
Mhm.
construction of or aesthetic observers, these kind of things, which is a very nice and teachable, let's say, theory, right?
Mhm. Yeah, definitely. So, well, there are two things. So, the concept of observability and observer design is also possible in discrete time. So there are already results for that. And we use that also in the data-driven context to find stabilizing output feedback controllers. So in the
Okay.
case where I do not have, like here, measurements of the state of my system,
Mhm.
but I attach some output equation, so I do not measure the full state, but only part of
Partially.
it.
Yeah.
Um, so there, an established idea, for instance, to construct an output feedback controller is to attach an observer together with a state feedback that feeds back the estimate of the observer rather than the state of the system.
Mm-hmm.
So that idea we indeed used also yeah, in data-driven control using output measurements. So in principle, one can do that both in continuous time and discrete time. So discrete time is not an obstacle for that, I would
Okay,
say.
great.
Um, yeah, but maybe one thing to note is that when one talks about data, it's very natural to talk about discrete time systems first
I agree.
because
I agree. Yeah.
because of these samples, right?
Yeah.
So
Yeah.
it's very
Yeah.
natural to collect samples from a discrete time system.
Mhm. Yeah.
So that's why in the simplest cases, we start always from discrete time models. But I must say that there are also extensions to continuous time.
Okay. Maybe okay. This is great as well, but somehow are already data driving. Let's say Lubenberg observer. I don't know. This state and observer controls, right? This I don't know how to say in English, but this is called is Lubenberg
Yeah,
observability. Yeah,
Leuenberger.
right.
Yes.
Lubenberg. Yeah, yeah. Can you construct something like that based only in data?
Yes.
Uh,
Yeah. Yeah. Yeah.
okay.
Definitely. So there's a paper I wrote a couple of years ago together with Vikas Mishra
Hmm.
in the CDC. That studies this problem indeed. The problem of constructing a Leuenberger observer using
Perfect.
data.
Okay,
Indeed.
that's very nice.
Thanks.
Okay, thank you.
Are any other last questions for Hank? Uh, if there are no further questions, we would like to really appreciate, thanks Hank for your talk. Thank you for agreeing to meet with us. Thank you so much for your nice talk.
Thank
And
you very
thank
much.
you all for attending to the seminar. And that's it.
I
Yeah.
thank you. We keep in touch. Thank you,
Yeah.
Hank. Nice talk. Thank
Thank
you.
you. Bye.
Thank
See
you
you.
so
Bye
much.
bye.
Thank you. Thank you all for your attendance. Again, thank you.